the Boltzmann distribution is really important because it allows us to explain the effect of a catalyst and also change in temperature on the rate of reaction. So, it's highly likely you'll be expected to draw a Boltzmann distribution. What it does is it plots the energy in a sample of atoms or molecules. So, if you think you've got a sample, I've got a reaction going on, I've got a little pot. In my pot, I can do a plot of the energies of how the energy is distributed amongst the molecules. And it comes up as a little... So, shall we give it a go? The way to start, put your axes on. Okay, so, Boltzmann distribution, so we just say... so what we'll say is, the particles in a gas travel at different speeds. So they have different kinetic energies. The Boltzmann distribution shows how the energy okay, I kind of think I'm going in a circle with that sentence, but anyway. Okay. Yeah. Oh, I missed out T. Okay. That's it now. Yeah. I think it's there for wrong. Yeah. And there's some sheet as well. Okay, so how can we draw it? Right. So you start off with your axes, like so. On the y-axis, it goes the number of molecules with the energy. So that's number of molecules. Goes here. And then along this axis goes energy. Right, so in blue, I will put the plot, and we'll also make a note of what we need to watch out for. So this here is energy 0. And my energy gets higher as I go along the x-axis. And then the number of molecules is plotted here. Okay. So, at 0 energy, there are 0 number of molecules. So no molecules in my sample have a 0 energy. Yeah? As my energy increases, more and more molecules have it. So it kind of goes up like so, it peaks, and then it goes down like so. So it has a steeper bit here, and then a gentler slope there. So the most molecules have this energy here. So most of them have that energy going down there. And then let's go, oh, and notice it doesn't hit this axis down here. So fewer molecules have a high energy, few molecules have a very low energy, and most molecules are in this average energy. Yep. Cool. So shall we just write little points to note? So points to note. The curve is not symmetrical. So I don't have like it's not like that. It's kind of steep here and then gentle there. At higher temperature, the curve is flatter. So it's a more gentle gradient. So that is at temperature. If I label that at low temperature, what I'll do now is in red, I've got how my distribution changes at higher temperature. So at higher temperature, it starts off at 0, it goes lower than this, it peaks, and then it goes like so. So in red is if I increase the temperature, that is at higher temp. Now I doubt you can read that. I'll try that green. At higher. There. So the area underneath the curve, if you do A-level maths, the area underneath that tells you what? What does the area under the curve represent from integration? If I was to integrate this, what would the area underneath this curve tell me? That would tell me the number of, yeah, brilliant, that would tell me the number of molecules. So, just because I've increased the temperature, does the number of molecules change? No, I've still got the same number of molecules. So at higher temperature, it still starts at 0, but can you see that my more molecules, this is now my average temperature, isn't it? It's now higher, which is now here. At a lower temperature, it's down here. That's it. So, if I now put on here, that arbitrarily, I'm going to say is my activation energy. There, for the reaction. So, at lower temperature, that number of molecules can react. So, at low temp, these molecules can react. They have an energy higher than the activation energy. Yeah? At higher temperature, not only can these react, but also these can react. So at higher temperature, both green and blue areas can react. So it's really important, if this comes up in the exam, to label your diagram, make it really clear. That's what I'm saying. So this demonstrates the effect of temperature. So at my higher temperature, can you see how many more molecules can react? Because this is my activation energy here. At higher temperature, these and these can react, but at lower temperature, only my blue guys can react. So the key points to know, both curves start at 0, 0. Can you see that it peaks, the red line peak is lower than the blue line? Yeah. But this line carries on higher. than the blue line. So you've got to be happy drawing these and make sure they're labelled up, because otherwise, you can explain this quite well. So we're going to just put one more line on. Let's go for it. How will my activation energy change if I introduce a catalyst? It decreases it. So if I'm now going to put in green a line which shows my activation energy with a catalyst. So in this is my activation energy with a catalyst, which is that. So suddenly, all of these extra molecules can react with a catalyst. So this area represents the additional molecules that can react with catalyst, like so. So the Boltzmann distribution is able to explain really clearly how temperature changes the rate of reaction and how catalyst changes the rate of reaction as well, in terms of the number of molecules that can react.